Sorry about that. It is a pleasure for me also to introduce to you Professor Jacob Mostovoy from Departamento de Matemáticas del Cinvestav. He's a pretty good friend of CIMAT, pretty good friend of all of us, and under his leadership, we are now getting together all these people who make algebras, non-associative algebras, Lie algebras, Jordan algebras. Are very grateful to Jacob for his, for the organization of all these meetings for all of us. Thank you very much. It's a pleasure to have you here.
Bueno, aquí está bien. Okay, so it's a great pleasure being here. Many thanks for inviting me. The subject of this talk is kind of slightly exotic. I mean, this whole subject of rocks is slightly exotic, or at least I used to think that it was exotic. It's really probably not as exotic, and the whole exoticity is just in the name. So let me start with some definitions, if I can. Well, the good thing is that I have few. Okay. So what is it about? So rocks. A rock is a prime example of a set with a self-distributive algebraic operation, and rocks somehow axiomatize the operation of conjugation in a group. So if we forget that the group that there is a product in a group, and we only remember that there is the operation of conjugation, let's try to formalize what the most important properties of the conjugation are. And there are basically two properties. One of them says that conjugation is invertible. Basically, this is the property number one. I mean, if you conjugate by A and then conjugate by A inverse, you get the same thing. And the second property is what's called self-distributivity. And here it is. So I don't think I mean, let's even write it down. If you want, I mean, since it's so important, I'll write it down. So X conjugated by Y and then conjugated by Z, what is it? Is Z inverse X to the YZ, which is Z inverse Y inverse X YZ. And on the other hand, if we write down X conjugated by Z to the Y conjugated by Z, well, we get Z inverse YZ inverse, then we get Z inverse XZ, then we get Z inverse YZ, right? So this, of course, is nothing but Z inverse Y inverse Z. So these Z's, they just cancel out, and we see that this thing is the same as this thing. So I have to prove, one has to prove something, right? So here's a proof of something. So the idea is, I mean, the question is, so suppose we have this operation which behaves like a conjugation, in the sense that it's invertible, and it's self-distributive. Is it true that this operation comes from a conjugation on a group? And the answer is no, no way. It doesn't necessarily come from conjugation. And a set with an operation that satisfies these properties is called a RAC. So, instead of giving you examples of RACs, I mean, people really like these self-distributive operations nowadays. But I don't. I mean, somehow this whole talk is about how to get rid of self-distributivity and get back to multiplicative interpretation of these objects. So one intermediate step from self-distributive things to the world that we know is what's called introducing what's called augmented RACs. So the definition of an augmented RAC is, on the surface, it's very different from the definition of a RAC. Well, actually, I'm running fast. Let me just say why it's called RAC. I mean, it's really a strange name. So, a strange name has its reasons to be. RACs were invented first, probably because many people invented them. So the first mention of the word RAC, at least, was by Conway. So they were invented by Conway and Wraith, who were like high school friends. And it was probably Wraith who started this whole thing. He was thinking how to axiomatize conjugation, and Conway actually wrote something about it. So Conway defined RACs, and he wrote them as RACs with W. And the word RAC comes from the expression rack and ruin, which means whatever is left after some catastrophic event. And the idea is that the catastrophic event is that we forget the multiplication, we only remember the conjugation. And this is like a ruin of a multiplication. Well, yes, it does. I mean, of course, this W actually stands for this W, for Wraith. So really, these objects were, I mean, Conway was being nice. He named them after his friend, but then some illiterate people came. I mean, none of them is in the audience, so it doesn't really matter. So they modernized the spelling of RAC and they raised the W. So this was a disaster for the subject, because I mean, it's really important to have a good name. And RACs, well, you know what RACs are, estanteria. It just has no romantic feeling to it at all whatsoever. So nowadays in the theory you have objects called shelves and things like this. So it really went to the wrong direction. But anyway, I mean, I really would like to call them RACs with W, but this sounds a bit old-fashioned. I mean, it sounds the same, actually. So, I mean, when I say RAC, I say it with W. Okay, so Conway and Wraith, they invented RACs, and probably, I'm not quite sure, probably it's from there when the applications of RACs in knot theory started. Then, well, there were several people who came up with the same idea. So you have works by Joyce, and he was actually writing about a special type of racks called quandles. I mean, if you've heard the word quandle, it's from this science. Joyce, then Matveyev. Matveyev called them distributive groupoids. And then there was Briscorn. And Briscorn called them automorphic sets. So every time there was a new name because like nobody really cared about these racks. So they're an exotic subject. But now finally people realize that this is a subject of interest. And the reason why it's of interest, it's that like it turns up in many subjects. When we go on to augmented racks, I'll give you some examples. But let me just say that racks have turned up in knot theory. So in knot theory, they're actually quite important. They give you, each knot has a fundamental rack, like a fundamental group, but stronger. And this fundamental rack of a knot really classifies knots. It's a very strong invariance. So we have knot theory. We have theory of Hopf algebras, the structure theory of Hopf algebras. And there you have, I mean, if you want to see how racks turn up in the theory of Hopf algebras, you should check the papers by Andruskevich and Grania. So apparently there is some, I mean really when you try to classify Hopf algebras, you run straight into racks. I mean I'm not going to talk about this, I'll mention how they turn up in knot theory. And there are also racks, they appear in this science which is called set theoretic solutions. Set theoretic solutions to the Young-Baxter equation. So it turns out that racks, they provide a class of these set theoretic solutions. This is also somewhat more mainstream than racks themselves. So, okay, but let me give you another definition first, that of an augmented rack. So an augmented rack really comes from the idea that you should actually try to reconstruct the product on a rack. So suppose you have a rack and suppose it really comes from a conjugation. So what kind of, I mean, what is the group on which it is it works as conjugation? And this is the answer probably. So if you have a rack and this is the set of all elements of the rack, well, you're supposed to read this part first, and then this part. Well, you've already done this, right? But anyway, so forget about it. So suppose we have a rack, and let's try to think that it came from a group. So what is the group? So we take a generator for each element of the rack. For each xi, you have this tau xi, and we impose these relations. And these relations mean that the operation in a rack really is a conjugation in a group. So you can take this tau xj and take it to the left. So what it says is that the conjugation by tau xj of tau xi is the same thing as conjugating as applying this as this operation, as this rack operation. So rack operation is conjugation. These are the relations on the generators, and what you get is a certain group, and you get a map of your rack into this group. Because like each generator goes to the each element of the rack goes to the corresponding generator of this group. But this map is not going to be surjective, it's not going to be injective. I mean, we did what we could. We tried to reconstruct the multiplication. It didn't quite work out, but something worked out. So what happens is that this group called the associated group of the rack, it actually acts on X. It acts on the rack. And, well, this action is kind of obvious. I mean, in the sense that you have a generator for an element of the group. So the generator tau xi, it's supposed to act on some xj. Well, how can it act? Well, the only possible way is xj to xi, right? Conjugating by xi. And it turns out that, I mean, we define this action on the generators, and it turns out that it extends to the whole group. So the rack X this way becomes a GX set, and the map from X to GX is a morphism of GX actions. So this motivates the definition of an augmented rack. So we take, we have a set X, and we have a group G. And G acts on X, and we have a morphism of G actions from X to G. Right? And there are other words for this. So probably a better word for this kind of object is a crossed G set. But I prefer saying augmented rack because you see the augmented racks, they form a category. And this category of augmented racks, it doesn't make any explicit mention of the group. I mean, you can have morphisms between racks with different groups. So we can't say, if we say crossed G set, we already specify this G. So so the word augmented rack is good for is better for speaking about the category of augmented racks. So actually, once I mention the category, so what is the category? So suppose we have an augmented rack. So this is a G set with a morphism of G actions from X to G. So here G acts on itself by conjugation, and we have X prime and G prime. So a morphism in this category of augmented racks is a commutative square like this, where this is a group homomorphism, and well, there is an obvious notion of what it means for a G action on X to be mapped into a G prime action on X prime. So, I mean, as I point out here, if you have an augmented rack, then this set X becomes a rack. So this is, if this map is pi, you take X to the Y. I mean, it's written there. You take the element, you take the image of Y in your group G, and well, it acts on X, right? So now let me go to examples. I mean, all this is abstract nonsense so far. Let's make this abstract nonsense concrete. Yes? Well, I didn't hear you very well, but I think that you're asking that you want me to say that The associated group functor is the adjoint to the conjugation, to the functor of taking the conjugation rack. Yeah. Right. Yeah, and they're adjoint functors. Yeah. Yeah. So so it's quite important that given any rack, you can think of it as an augmented rack in a canonical way. So I prefer to think about them as augmented racks. So here are some examples. And of course the first example is trivial as usual. So it's not, if you take a conjugacy class in a group, then a conjugacy class acts on itself by conjugation. So it's a rack, and the inclusion map of the conjugacy class into the group is an augmented rack. Actually, a disjoint union of any number of conjugacy classes is also an augmented rack. So already this says that the tracks are more than just groups. So we're talking about conjugacy classes here, but it's more than just conjugacy classes. So the second example is also kind of it's probably is a hint of why it can be of some interest. I mean, people don't speak about root systems as racks because they have the word root systems. I mean, why introduce special names for something that already has a different name? Here, a root system, I mean, we don't really need too many properties of a root system. So we take a vector space, so S is a set of vectors. Well, X is a set of vectors here. X, a set of vectors that span some vector space, space V, and with the property that X is invariant, is stable, let's say, under the reflections in the hyperplanes perpendicular to elements of X. So, for instance, if we have a vector in X, and we reflect it in this line, we get minus X, right? So, together with each element, with each vector here, well, X is a small x here, we have minus X. And, well, a correct definition of a root system involves another couple of properties, right? So we also want it to be reduced and integral, but here these two properties are sufficient. So to each little x in big X, we can associate the reflection in the hyperplane perpendicular to X, right? And we take the group which is generated by these reflections, and this is the Weyl group of the root system. And this Weyl group, this Weyl group, it acts on X, obviously by reflections. So this is an augmented rack. So root systems are augmented racks. Another example from Lie theory is the exponential map. So the exponential map, how does it work? So the action of a group, of a Lie group G on the corresponding Lie algebra is called the adjoint representation, right? Is the adjoint representation. So x to the y here is going to be just the adjoint by of what? Of xy by xy of x. All right? So we just conjugate by the exponential of y. So that's how the exponential map gives you an augmented rack. So these, again, I mean, these three examples, they can all, I mean, we all talk about them all the time, but in a different language. But this one is kind of more genuine somehow. This example has been of great use in knot theory. And so here the group is the fundamental group of a knot. And this is just the fundamental group of the complement of the knot. What is it? So if you have a knot, well, I think I have it drawn some. Right. So this is a knot. All right. This red knot is a trefoil, and it's actually not just a knot. It's what's called a framed knot. And the framed knot is, well, it's not an. When we think of a knot is an embedded interval, right? Interval, well, circle. And this is not just an embedded circle, it's an embedded ribbon. So it's an embedded very thin ribbon in R3. So together, one side of this ribbon is the knot, and the other side of this ribbon is a parallel copy of this knot. And it's more or less the same when you speak about knots to talk about embedded circles as embedded ribbons. The only new thing that we have is the number of times that this ribbon can twist around itself. So this is what's called a framed knot. So it doesn't have much more information as usual knots, but it gives us some additional algebraic freedom. So, well, what's the fundamental group of a knot? Remember, if we have a knot, I will draw some very important knot. So this is the trivial knot. So we choose a point outside the knot, and we consider the homotopy classes of all paths from this point to itself that don't cross the knot. I mean, these paths then they can cross themselves, but they don't cross the knot. So the homotopy classes of these paths are the fundamental group of the complement of the knot, and the inverse of each path is the same path which goes backwards, right? This is because we're considering paths up to homotopy. Then it can be contracted to the constant path that stays at this point. Well, I guess, I mean, it's all common knowledge. So the fundamental rack of a knot is something very similar to the fundamental group, but different. Instead of paths that go around the knot or that don't cross the knot, we consider paths that start out at the mark point, and they hit the knot in the end. So they hit the knot at the end, and they enter the knot in this direction, which is indicated by the ribbon. So these things, the homotopy classes of these paths, when of course we allow this endpoint to move along the knot. This is part of the homotopy. So these homotopy classes, they form the fundamental rack of the knot. The question is, what's the operation on these things? And the operation is this one. So first we have to give a map from these things to the fundamental group, right? So it's this one. So we take this path that hits the knot, and instead of hitting the knot, we just add the loop. So this path is start out here, get to the knot, get very close to the knot, and then instead of hitting it, just go around it, and then go back by taking the same path. So this is the map from the rack to the fundamental group. And we have to specify also the action of the fundamental group on this rack. And it's this one. I mean, what does it mean? So suppose we have this path and this element of the fundamental group. So the new path, the action of this loop on this path just means precompose this path with this loop. So we first go around here, we come back to this initial point, and then we go along the second path and hit the knot. So that's the structure of that's the fundamental rack of a knot. It looks a little bit silly. I mean, I totally agree with you. But it works wonders, in the sense that it's really not very difficult to prove that the fundamental rack of a knot is a complete invariant of the knot. It's also...
I feel quite understand that. So you have these... Thank you. So you have these, this path that goes from your point to a point in the knot. But how do you decide which path? Because I mean that path looks particularly simple. I mean, it seems like
well,
I can touch the,
here I was just too lazy to draw, so I kind of reused the previous slide. In general, what do we have? So what's our general situation? We have, so we want the action of pi 1 of R3 minus the knot on this fundamental rack X. So this is the base point, this is the element of the rack. I mean, I assume that this is the framing. And now suppose I have any horrible, dreadful loop that goes around here. So first I go around the loop, and then I go along this path.
Oh, so the path is the guy in the rack. So that's
yeah. So this thing. Okay. So this path is the element of the fundamental group. This is the element of X of the rack.
Okay.
So that's and this thing, the concatenation of these two things, is again the element of the rack.
So the element of the rack is the rack consists of homotopy classes of paths from the base point to any point.
To any point on the knot. And the notion of homotopy involves moving this endpoint along the knot.
Okay.
This point is fixed and this point is movable. So people actually have, I mean, it's not really, this example is not really the subject of this talk, but it's a very important example because people have extracted some very concrete information from this construction. So you can construct some knot invariants from this, and these knot invariants really work. This is really, and this is really the whole point of it. This is something useful. And actually, the same people who worked with knots, they realized that that you can do something something rather interesting with these racks. You can define homology for racks. And well, there are different versions of homology. There is homology for racks, there is homology for quandles, and it looks rather strange. I mean, it looks strange to my eye somehow. So what people do, but again, I mean, it's a perfectly sensible construction, which is something that I'm going to explain. I mean, when someone claims that to explain something is that, wow, I understood something, so now I can preach the same thing, all right? well, all this talk, of course, is that I understood something and I'm preaching something, right? But really, I mean, let me show first what the homology for X is. So, if you have a rock, not necessarily, I mean, I'll forget about the augmented racks for a second. So we take any rock, and we can associate with this rock something that knot theorists have called rock space. And the rock space is a topological space with an explicit cell decomposition, and the homology of this rock space is going to be the rock homology. So this rock space, it works as follows. It has only one vertex, and then it has edges for each element of the rock, A and X, and then it has square cells of this type. A, B, B, and then A to the B. These are the two-dimensional cells of this rack space, and then if these two-dimensional cells manage to form a cube, then you fill in this cube and it becomes a cubical cell, and so on. So this cubical space is somehow defined only by the squares, and then you can write down the explicit chain complex that defines the rack homology, and it's all a little bit strange. So, I mean, to tell the truth, I don't think that rack homology has been of much.
Homology, it doesn't have like any relation with like the group. I mean, you take a group and you associate this cohomology. You look at this cohomology as a rack. You have a group and then you look at this cohomology as a rack. It's going to be something completely different, or it's going to be related?
Well, it's kind of different. It's kind of somewhat different, yes. It's not because...
like this is not like the classifying space of a group or anything like that?
No, the rock space... I mean, if you look at the notation, it is slightly confusing because it's the classifying space. They call it the classifying space for a rock. But it's not the classifying space of the conjugation rack of a group is not the same thing as the classifying space of a group. It's somehow, I mean, you should think of this conjugation as being some sort of a local system. It's some sort of coefficient, cohomology of the group with coefficients in the conjugation local system, whatever it means. It probably doesn't mean anything. All right. So, okay. So let me now go to the subject of the subject of my talk, which is multiplicative graphs. And the idea of a multiplicative graph is a bit silly, as all good ideas are. So on graphs there are all sorts of products. And one of these products is the Cartesian product of the graphs. So what is the Cartesian product? Well, it's written there, like the number of, so the vertices of the Cartesian product of two graphs are the are pairs of vertices of two graphs. Now, as you might notice, if you know anything about graphs, these are not really graphs. These are directed graphs with possibly with multiple edges. So for me, a graph is just a pair of sets, vertices and arrows, and each arrow has the beginning, which is called S for source, and the end, which is called target. So that's it. So this is what a graph is for me, and this is the Cartesian product. So on vertices, it really is the Cartesian product. And on edges, it's this thing. So really, what happens here is that we think of our graphs as some kind of simplicial complexes. And we take a Cartesian product of these two simplicial complexes, and we erase the two-dimensional cells. This is what happens. Now, this Cartesian product is not really a categorical product. I mean, graphs form a category, and the categorical product of a graph is of two graphs is something different. But this is something that graph theorists call the Cartesian product. And this Cartesian product is obviously associative because, well, it's, for instance, because of what I said, that it's just a real Cartesian product with the cells of extra dimensions killed. So the reason why it's written as a square is that if you take the graph with two vertices and one edge, this one with one arrow, then this graph, well, call it Q1. Then Q1 product, Cartesian product with Q1 is going to be this graph, this square. All right, so Cartesian products of the Cartesian powers of this thing are just going to be the one skeleton of n-dimensional cubes. Okay, so a Cartesian multiplicative graph, well, is something that is natural to, in a way it's natural. I mean, it's the same definition as a, say, a semigroup, right? So it's just a graph morphism. A graph morphism, I mean, a graph is a pair of sets, right? And so we consider this category of pairs of sets, and morphisms are commutative diagrams of these pairs of sets. So the set of vertices, I mean, oh, sorry. So the vertices of the Cartesian product of a graph with itself, they're just vertices cross vertices. So this multiplication in dimension 0 it's just vertices cross vertices goes to vertices. This is what it is. So it's actually a product, an associative product. And what is it on? What is it on edges? So okay, so G already. I think G here is the semigroup of vertices. So we have a product on the set of vertices, and we have an action of vertices on edges and an action of edges on vertices on the other side. So we have a two-sided action of the group of vertices on the set of arrows, and this maps to the product on G. Now, really, this is slightly too general. So, what I'm really interested in are graphs whose vertices, multiplicative graphs whose vertices form a group. So, if you have a group-like graph, then we get immediately an augmented rack out of this thing. So how come? So the vertices of a graph, well, they are elements of a group, and one of these elements is the unit, right? So we have this vertex which is the unit of the group, and we consider the set of all arrows that emanate from this unit. And we have two actions of vertices on this set. One is, well, not two actions on this set. We can multiply by the elements on the group on the left and on the right. So if you multiply by G inverse on the left and G on the right, well, if we have the unit element in the middle, then it will just cancel out. So you have an action of your group G on this set. All right, and this set maps into a group. This group acts on by conjugation. So this is an augmented rack. And the end, this end map, is just the augmentation in the rack. So once you have a group-like graph, you have an augmented rack. And if you have an augmented rack, you have a group-like graph. I mean, it's totally straightforward. Yes. A group-like graph is a multiplicative graph whose vertices form a group.
Okay.
So it's only this. So okay. So far we haven't really done much. So multiplicative graphs are the same thing as augmented racks, but group-like graphs are the same thing as augmented racks. But we also have the notion of a monoid, which is quite different, right? I mean, if your vertices only form a semigroup, then you don't have an augmented rack. You have a different notion. And I'll show you an example of such a situation, which is of interest actually in knot theory. All right, I can't remember what follows. No. Okay, so here's an example of a group-like graph. You take a Lie group, and you consider, I mean, we forget about the topology on the Lie group. We just think of it as a set of its points. And the elements of the group are the vertices, and the arrows are just pieces of geodesics from one point to another. Well, we parameterize them by length. So this is a very simple example, but the nice thing about it is that both maps, like the source map and the target map in this graph, are vector bundles. And this is kind of maybe slightly unexpected, but I mean, if you think about it, it's completely trivial somehow. So this indicates that the Lie theory of these group-like graphs has something to. Well, this indicates the direction of the Lie theory for these graphs. I mean, it's really easy to construct, and it gives you racks, and it's called some sort of special kind of racks. So, okay, we've seen an augmented rack, which was the fundamental rack of a knot. So how does it work in the setting of multiplicative graphs? So here, our vertices are the elements of the fundamental group. These are two vertices, and this is an arrow. So an arrow is a path outside the knot which hits the knot once. It has the misfortune of hitting the knot exactly once, but it behaves nicely outside of that. So in a way, it's a bit more natural to look at the fundamental rack of a knot like this. So somehow you can think of a multiplicative graph as the following thing. So the vertices are elements of your group, and the arrows, they're some sort of transformations from one element of a group to another element of the group. And this transformation in the case of the knot group is just the cross the knot once. This is what we allow here. Okay, so this is the universal example of a multiplicative graph, really. I mean, I use the word cubical complex here, but the most scientific word for it is a precubical set. So precubical sets are basically, well, you should really think of a space which is subdivided into cubes, and for each cube you have an an identification of this cube with a standard cube in Rn. I mean, you know which is the first direction, second direction, third direction, and so on. So this is a precubical set. Now, precubical sets, well, they're very important in topology somehow. You know, Serre used, I think he used precubical sets in the in his theory of what? I mean, when he constructed the Serre spectral sequence of a fibration, he used cubical fibrations. So the good thing about these precubical sets, if you take these two spaces subdivided into cubes and take a product, then a product of a cube with another cube is again a cube, right? So this way, so these cubes, these cubical structures, these precubical sets behave very well with respect to the Cartesian products. I mean, if you take two simplicial complexes and take a product of two simplicial complexes, well, a product of two simplices is not a simplex at all, right? So, I mean, when you're trying to prove the Eilenberg-Zilber theorem, for instance, it's exactly this problem. I mean, you have to subdivide, how to subdivide a product of two simplices into simplices again. So, in the simplicial world, the solution to this is considering simplicial sets, adding degeneracies. It's like a whole subject in its own, but precubical sets are these things, and they behave well with respect to products. So suppose we have a precubical set with a product on it, and the product sends an I cube, a product of an I cube with a j cube, to some I plus j cube. So then, if you consider the vertices and the edges of such a precubical set, then you get a multiplicative graph. Now, I mean, it might look abstract and slightly exotic, but it really isn't, because any augmented drag produces a precubical set with a product on it. So what do we, how do we produce a cubical set out of a multiplicative graph? Well, you can just take, you consider your graph as a topological space, and consider the free group generated by all the points of this space. I mean, it's going to be a free group with a lot of generators, but you can put a topology on this group. You can subdivide it into cubes, and you can consider the following relations. The following relations. So the product of a vertex G with some point on an arrow x in this free group should be equivalent to the action of this vertex G on the element x, and the same thing on the right side. So, okay, well, I mean, I'm saying free group. Really, I want to consider the free monoid. I don't want to talk about inverses here. I'm sorry. So you take this free monoid, you take the quotient by these relations, and again you get a monoid. And it's going to be cubical because, well, because that's how it works. I mean, you started with a graph. You started with some graph. All right, and you take the free monoid generated by this graph. Let's say the gen x1 over here, x2 over here, x3 over here, and x4 over here. Consider these the words, for instance, x1, x2, x3, x4, right? This is a product in this free monoid. And x1 runs over an interval, x2 runs over an interval, x3 runs over an interval, x4 runs over an interval. So all products of this type, where x1 and x3 live here, x2 lives here, and x4 lives here, they run over a four-dimensional cube. right? So this is how all these products, this is how the free monoid generated by a graph is subdivided into cubes. That's how it works. And I mean, if you look at these relations, they also preserve these subdivisions into cubes. So what you get is some sort of a big cubical space with a product on it, because it's a quotient of a monoid by some relations. So on this monoid, you have an action. You have an action by this group G, by the group of vertices of the graph Q, and all right. And the quotient turns out to be the same thing as the rack space of this augmented rack. So what did we do really here? So we take a multiplicative graph. We associate with this multiplicative graph a cubical product, well, a product on a pre-cubical set. And again, so this multiplicative graph becomes just the one-dimensional skeleton of this product, and we take the quotient by the action, by the group of vertices. By the action of right. So again, well, maybe it really, I mean, to understand how it really works, you just have to consider, well, you have to consider some example, try to work out how it actually works. But again, the idea is that we start with this funny multiplicative graph, which is not really multiplicative, and then complete it to a real multiplication on some really big space. And then this big space, well, it covers this rack space. So that's how it works, how these things work via multiplicative graphs. Now, the reason I was interested in these things was not really trying to define the rack homology, was not looking for the rack space, but trying to define Lie theory for these objects. And Lie theory, well, it works in, well, there are several things that can be understood as Lie theory. So for normal people, well, for normal people, I mean, for normal people it doesn't exist, right? But probably the most usual idea of what Lie theory is that you have a Lie group and you associate with it a Lie algebra, and passing from the Lie algebra, from the Lie group to Lie algebra and back is how Lie theory works. Well, the basics of Lie theory. I mean, the interesting parts of Lie theory are different, but again, we just are trying to do the basics. It turns out that that Lie theory, I mean, these basics of Lie theory, they work in some very general circumstances, and somehow there has been a lot of noise around this Lie theory for racks, and it had to do with the so-called Leibniz algebras. So at some point, like the story about the Leibniz algebras is as follows. At some point, Jean-Louis Laudet, maybe like 25 years ago, defined some sort of a different homology for Lie algebras. So the usual way to define homology for Lie algebras is that you take your Lie algebra, you take the Chevalier-Eilenberg complex, and which consists of exterior powers of your Lie algebra. And then there is some differential and all that. So Lodey noticed that instead of the Chevalier-Eilenberg complex, instead of the exterior powers, you can actually take tensor powers without any antisymmetrization at all. And then you also have a certain differential on this complex, so it gives you some homology theory, which is quite different from the usual Lie homology of Lie algebras. So he called it Leibniz homology, and the interesting thing about this Leibniz homology is that you never really use the fact that your Lie bracket is antisymmetric in the definition of this Leibniz homology. So Lodey said, okay, let's consider things that look like Lie algebras but are not antisymmetric. Let's call them Leibniz algebras. What are these things? What are the corresponding, what are the analogs of Lie groups for these strange objects? And then there was this really like years and years people trying to answer this question, which is really quite obvious in a way. I mean, somehow this whole subject was motivated by Lodey himself, not by his ideas, but by his person. Because, well, the answer is in a way obvious. For some reason he didn't like it. And the answer, well, he actually gave the answer himself. So he explained what a Leibniz algebra really is. And a Leibniz algebra really is a Lie algebra in some funny category. And this funny category is this Lodey-Pirashvili category of linear maps. And so this is what it is. You have, instead of vector spaces, it has pairs of vector spaces with morphisms between them. And the important thing about this category is the tensor product. So you can think of this object in the Lodey-Pirashvili category as having this is having degree 1, Ut having degree 1, and this thing having degree 0. So in degree, so the product in degree 0 is just the tensor product of degree 0 things, and in degree 1 it's this kind of thing. So I mean, you can notice the similarity with the Cartesian product of graphs, right? It's a little bit like this. So instead of tensor product, you write down Cartesian product. Instead of plus, you write disjoint union, and you get the definition of a multiplicative graph. It's really very similar. So, but what it really is these are one jets or one germs, sounds similar, of differential graded vector spaces. So here a differential graded vector space is graded by non-negative degrees. So and the grading is homological. So what is a differential graded vector space? You have V0, V1, V2. All right. So this is a differential graded vector space for me, and there is a tensor product of differential vector spaces, and for instance, the tensor square of this differential vector space will be V0 tensor V0. Well, I mean in degree n, it's going to be the direct sum of Vi tensor Vj, where I plus j is n. So this is the degree n part. So what you can see here is that we're talking just degree 0 and degree 1 part of a product of two differential graded vector spaces. So this is the same thing as a multiplicative graph being well, or a graph simply being a one-dimensional skeleton of a cubical space. This is the same idea behind it. So, but Lade and Pirashvili, they didn't talk about multiplicative graphs. They were only interested in this thing. So we have this tensor category, and in the tensor category we can permute we can flip the factors in the tensor product, and the tensor product is associative, and we can define Lie algebras in an arbitrary tensor category. And Lie algebras here so we can define algebras to begin with in the Lade Pirashvili category, and these can be, in particular, Lie algebras and Hopf algebras, and everything works in the very same way. I mean, you have the Poincaré-Birkhoff-Witt theorem, you have Milner-Moore theorem, so there is really no new theory to develop. I mean, it was developed by Lade and Pirashvili, I mean, in their paper, but I mean, this whole paper boils down to the observation that Leibniz algebras are Lie algebras in this category. So, of course, when you write down this definition, it looks kind of, it has some details. So, a product is a product in degree 0, and in degree 1 is this H bimodule structure. And what's a coproduct? I mean, it's on degree 0, it really is a coproduct, and in degree 1, it's a two-sided coaction. And this coaction and this coproduct have to be related in this way. So this is what a Hopf algebra is. Now, an antipode, I don't know if I wrote down what an antipode is. I didn't. But I mean, there is a way to define an antipode in a Hopf algebra. So this is what a Lie algebra. Okay, so here I have the definition of a Lie algebra in the Lade Pirashvili category, and it's just what? It's a pair. You have a Lie algebra, and you have a right module. I mean, I say right module. It could be a left module. It doesn't really matter. It's just Lade and Pirashvili spoke about right modules, so I follow their notations. So, and this is supposed to be a map of a G-equivariant map. So this is how the Leibniz algebra structure works. You take two elements of this module. M is, so this module becomes a Leibniz algebra. You take two elements of this module, and then you take one of these elements, you send it to the Lie algebra G, and act on the right by this element. And this way you get a Leibniz algebras, and all Leibniz algebras come from this construction. Again, this really looks like the augmented Dirac thing, right? For augmented Diracs, you have what, a set here, a group here, and an equivariant map here. It's all very similar. So, an interesting thing, a curious thing is that somehow people, when people talked about augmented Diracs, they tried to define the analogs of the group algebra for augmented Diracs. And well, I mean, it's not that the whole humanity tried it, a couple of people tried. But it turned out to be not so trivial to define the analog of a group algebra for an augmented Dirac. And if you think of augmented graphs as multiplicative graphs, it's actually quite obvious what to do. So, again, you have the arrows of this graph, you have the vertices, which form a group. So you map the arrows, you map each arrow to its end minus the beginning, which is the obvious thing to do. And then the question is, what is a coproduct? The products are, the product thing is obvious. The question is what a coproduct is. And on the vertices, it's the coproduct in the group algebra. It's the usual thing. And in degree 1 for arrows, the coaction looks like this. You take an arrow and multiply it by its end plus the beginning of this arrow multiplied by the arrow itself. And this way you get a B algebra in the Lodey-Pirashvili category. And this is something new. This is something that was not 100% trivial how to do it for racks. Now that I talk about it, let me say one thing. So I was kind of trying to make the point that behind all this science of multiplicative graphs, you have cubical sets. That really all this should be extended to cubical sets. And this thing doesn't work for cubical sets in general. Why? When you have a cubical set, so suppose you have a precubical set, precubical set, and you have a product from x cross x to x, then you take the cell complex, the cell complex of x, you have the multiplication on the cell complex generated by the cubes. So you have an algebra. It's a wonderful thing. You have a product on the cubical sets, and then its cubical chains become an algebra, but it doesn't have a coalgebra structure. Why not? Because the coalgebra structure, when you have a topological space and you have the topological chains, well, you get a coproduct which comes from the diagonal map. X goes to x cross x. And the point small x goes to the pair x, x. Well, this map is not cubical. If you map an interval to a square, the diagonal embedding would be this one. But it's not a cubical map. A cubical map would send an interval to some combination of intervals here. And it doesn't quite work here. So still, we can find, in dimension 1, we can find some sort of a cubical approximation to this map, which is, say, this one. Something like this. But when we try to get to higher dimensions, I don't think it would work at all. You can't make this thing into a Hopf algebra. But up to dimension 1, you can. And this is a bit surprising. I don't think it has been observed before. So this way, so this was a comment. So starting with a multiplicative graph, we have a B algebra in this category of Lodey and Pirashvili, and it really is a Hopf algebra if your graph is group-like. And the antipode, the antipode in the group algebra, the usual antipode in the group algebra sends G to G inverse, so we have to complement it with some antipode for arrows, and it's this one. It's kind of, don't ask me why, it just works out this way. Well, in fact, ask me why and I will answer, but you won't ask, so I will answer anyway. So, for a group, you have the notion of an opposite group somehow. The opposite group, it's just like multiplying vice versa by the inverses. And for a multiplicative graph, you can define an opposite multiplicative graph. And somehow this is how this opposite multiplicative graph works. So this gives you an antipode. It's not really an arbitrary construction. So There is one thing that you can do with a group algebra. So you start with a group, and okay, I'm sorry, I started a sentence and I never finished it. It was like half an hour ago. And this sentence was, what is Lie theory? And Lie theory is like many things. So one of the phases of Lie theory is you start with a Lie group and you get a Lie algebra, which is the tangent space at the unit. But another phase of the Lie theory, it turns up in the theory, in combinatorial group theory. So you started with a discrete group and you consider its low essential series, and the successive quotients of the low essential series of a group, they form a Lie algebra. So the commutator operation induces a commutator, induces a Lie bracket on these low essential series quotients. I mean, this low essential series science can be restated in terms of group rings. So if you, well, I don't know what follows. Maybe it's this. More or less. No, so if you have a group, if you have a group G, you can associate with it the group ring Q of G. And inside this group ring, you have the augmentation ideal, which is, I will write it as I of G. And this augmentation ideal, it consists of linear combinations of, so these are these are sum of Ki, Gi, where Gi, R, and G. And these consists, these are the linear combinations such that sum of Ki equals 0. So I mean, from here, from Q of G, you have, in other words, you have a homomorphism from Q of G to the rationals, which is just the sum of the coefficients, and this is the kernel of this homomorphism. So this is an ideal. And so you have I of G, and the square of this ideal is also an ideal, and then the cube of this ideal is also an ideal. So you have a chain of ideals inside each other, and it turns out that the associated graded algebra, you can take the associated graded algebra, sum of this direct sum of In modulo In plus 1. So it turns out that this is a Hopf algebra. So Q of G was a Hopf algebra, and this is also a Hopf algebra. But these Hopf algebras are quite different. This Hopf algebra has no primitive elements whatsoever. It only has group-like elements, which are the elements of G. This one has no group-like elements apart from the unit. But it has a lot of primitive elements. It's actually generated by the primitive elements. And this, and so the primitive elements is well, a primitive elements in a Hopf algebra, if you might remember, form a Lie algebra, because the commutator of two primitive elements is primitive again. So the primitive elements is the Lie algebra that comes from the low essential series. The Lie algebras of the low essential series. So this in a way, this sort of gives you a way of defining the low essential series without commutators somehow. This is an alternative approach to the low essential series somehow. So when you get a group G, this is a way to obtain a Lie algebra from a discrete group. So if you start with for instance, if you start with a free group, you end up with a free Lie algebra on the same number of generators. So somehow doing the theory of commutators for racks is is something that we cannot do. I mean, nobody managed to invent a decent commutator theory for racks. And there are various setups for general commutator theories, and racks don't enter there. But somehow they do enter into this setup. So we have this Hopf algebra of a group-like graph, and we can define the augmentation ideal for this group algebra and form the associated graded algebra in the Ladey-Pirashvili category. So how does it work? So on the left vertices, in Q of G, we just take the usual augmentation ideal, and in the space of arrows, we define the nth power of this augmentation ideal. We have to define this filtration directly in this way. I mean, A is an arrow, and V1 is an element of Q of G. V2 is an element of Q of G, and we want these two degrees to sum up to n. So really, all these degrees, they come from the augmentation ideal in Q of G somehow. And well, we just run the same machine. We have a filtration on this on this Hopf algebra, and on analog of the group algebra, and just by mimicking the same constructions as for groups, we get a universal enveloping algebra of a certain Lie algebra in the Ladey-Pirashvili category. And this Lie algebra, there's a question: what kind of Lie algebra is it? And we can describe it. I mean, it's not maybe particularly interesting, but even an augmented rack, it's not particularly interesting in the sense that it doesn't really give us anything unexpected. If you have the augmented rack, then somehow the lower central series of this group acts on the rack, and it gives you some filtration. And well, here it is described in terms of the augmentation ideals in these terms. So we have some sort of module of co-invariance of an augmented rack. That's all that is important, is that this Hopf theoretic construction for these multiplicative graphs can be interpreted in terms of augmented racks. Now, there might be, I mean, I could say more things about the Lie theory for multiplicative graphs. And I mean, you get some things like Maltsev completions, you get an explicit integration procedure for Leibniz algebras, which is, again, I mean, I stress it's nothing new. I mean, there is one particularly important Leibniz algebra, which is a Lie algebra. I mean, you take a Lie algebra G, and it is a Leibniz algebra, right? It's a Leibniz algebra that happens to be antisymmetric. And as an element of the Ladey-Pirashvili, as an Lie algebra in the Ladey-Pirashvili category, it's this. I mean, it's the map of the Lie, it's the identity map of a Lie algebra onto itself. So this is a Lie algebra in the Ladey-Pirashvili category. And if you integrate it, well, you get the exponential, you get the multiplicative graph, which is the multiplicative graph of geodesics in the, well, integration. So you get the geodesics in the Lie group G, which integrates the Lie algebra G. So, no. I mean, well, okay. I mean, I need... Okay, so really, I think of one parameter subgroups, but they have to be, yeah, sure. So this is how this important Leibniz algebra integrates, and arbitrary Leibniz algebras integrate to something very similar. I mean, I think it would be just too much. Probably this is just enough to just enough of notions for this talk.
¿Preguntas?
Yes, so I have a bad question. Yes, so I have a bad question in the sense of maybe not just being stupid, but also inviting even more terms into the conversation. So when this Hopf algebra that you've constructed, if I understood correctly, is co-commutative?
It's actually a very good question. So I constructed two Hopf algebras.
Okay.
So the analog of the group algebra for these multiplicative graphs is manifestly non-co-commutative.
Okay.
It's non-co-commutative because, like, the beginning of an arrow is different from the end of the of an arrow. But the associated graded Hopf algebra is co-commutative.
Okay.
Because modulo the augmentation ideal, the beginning and the end is the same thing.
So here's the terrible question. Whenever I hear about Hopf algebras, the first thing that comes to mind is non-commutative geometry. So is there some kind of like non-commutative version of an augmented rack or of a multiplicative graph that would somehow give rise to a construction similar to this that would give you a Hopf algebra that's possibly neither commutative nor co-commutative?
Well, the answer to this kind of questions is usually yes. Because, like, I mean, you can always invent something. But, yeah, I would think so. But,
like I said, it was
I mean,
a bad question.
what you really want is some quantum version of the same thing. And I think, yeah, the answer should.
They would give you like a quantum universe envelope.
But I don't have. Like, what you really want is some sort of a multiplicative graph over a quantum group, right? I would guess that it should be really easy, but I don't have examples in my hands.
Okay. Thank you.
Another question. I have one. It is really, I don't know, also a silly question. You mentioned what Lie theory is all about, and you said, okay, so we have a Lie group, and we have a Lie algebra, and we have the exponential map, and as a matter of fact, one of your examples was the exponential map as a rock. But it's also about looking at things that do not change under the action of a Lie group. You know, to look at invariants under certain kind of transformations. And then you recover the Lie algebra as the left invariant vector fields, for example. So you use the notion of invariance and left invariance in order to recover part of the algebraic structure. So is there something like this in here? At some point I thought, you know, you were using the augmented rack as a map from X into G, and you were motivated from the fact that when G is a group and it acts on X, then you have this kind of example with a map going in this other direction, X into G. And I thought, oh, okay, so you're going to look at what is the image, for example, of an orbit in the G space into this G, and it seems to be like a conjugacy class or something like that.
Well, a union of
But
conjugacy classes.
But then at some point I said, oh, okay, so it's going to be some invariants coming up, and in that sense, there were no invariants. Are there anything like those?
Well, you have coinvariants. Now, what's... I mean, somehow, what happens really is that, well, the question is vague, right? So the answer is also vague. All I'm saying is that all this science of augmented racks is really the replacing groups by some kind of graded groups and differential and graded objects. So it's basically making Lie theory graded, but only up to degree 1 somehow. So ideologically somehow it all should be the same. Invariants, everything should work more or less in the same way, but graded. So it's a vague answer, and this answer is yes. I mean, invariants. Invariants are behind everything here. Like you have a Lie group, you have a group downstairs, which means you're talking about invariants. When you have action, you have invariants, but I have to say that there are parts of the story which I would like to know, but I don't know. And when you say invariants, let me mention one problem that I see here, and when we define rack space, for instance. We take the quotient of some universal cubical multiplication by the action of the group of vertices, and the question is, what is the linear version of that? I mean, linear version in the sense of these Lie algebras in Lodey-Pirashvili category. So if you have a Lie algebra in Lodey-Pirashvili category, like degree 0, degree 1, you can do this same, you can perform the same construction. You can look at, as for X, you can construct a differential graded Lie algebra that extends this Leibniz algebra. So really Leibniz algebra is a piece of a differential graded Lie algebra. And then you can probably write down the Chevalier-Eilenberg complex, and you can look at invariants in this Chevalier-Eilenberg complex. And this will probably be some sort of an analog of the rack space. And these invariants is something that I have no idea what they mean. I would really like them to encode some sort of a Leibniz homology, but I don't really know how it works. I mean, yeah, invariants are all over the place and in strange ways.
Any other question? Well, let's thank Jacob again. We're going to have lunch at the restaurant in the hotel, and we'll be back at